Solutes. What's a solute? A solute is just a dissolved mass in a solution, which is, in this case, water, of course. So solutes are important to hydrology because in hydrology we're often concerned with water quality. Water quality is just that term that we use, as you may recall, for the chemical quality of water with respect to what we want to use it for, primarily. So we would look at the water quality with respect to drinking, or the water quality with respect to ecology, or even the water quality with respect to recreation. So the concentrations of solutes can be beneficial or they can be harmful. So when a solute is something we don't want in water and that can potentially be harmful or toxic, we would call that pollution. So we need to be able to perform mass balances not just with water, but with the chemistry in the water. So we need to look at the concentrations of chemistry in water. So we start with the concentration, we'll call C concentration, and then that has units of mass per volume. So that's the mass of the chemical per volume of water. And so it might be, say, in units of milligrams per liter. So say milligrams of chloride per liter of water. And often in the literature you see another way of expressing this, and it's approximately equal to what we would say is parts per million. And so rather than working with a mass per volume, we can look at parts per million as a mass per mass. So milligrams of a chemical per milligram of water, for example. And because water weighs about a kilogram, we can switch between one another. Now, if we have very high concentrations of chemistry, this starts to fall apart because the density begins to change. But for everything we work with in water quality, we can generally transfer between parts per million and milligrams per liter. So say I change this to micrograms per liter. A microgram per liter would be approximately equal to a part per billion. And of course, we can do parts per thousands and whatever we want. So we need to do a mass balance on this. And just like in the past, we did mass balances on volumes of water, masses of water, the amount of heat energy in water. We're going to do a mass balance on the dissolved concentration of a chemical in water. So rather than starting with our typical mass balance equation and working our way to the solute balance, I'm going to write down the solute balance equation, and I'm going to show you that it's really just mass balance. So on the left-hand side, we have the change in storage with respect to time, as we always have. But this time, rather than looking at the change in storage of, say, water volume, we're looking at the change in storage of the concentration with respect to time. So we have the derivative of C with respect to time, and I'm going to multiply that times the control volume. Remember, we do this balance on a control volume. So what did we have before? We have the change in storage with respect to time is equal to the mass flow in and the mass flow out. So I'm going to write that as the flow rate. Remember, we had the change in volume with respect to time was equal to the flow in minus the flow out. So we still have the flow in and the flow out, but now I'm going to multiply times the concentration of that chemical in the flow rates in and the flow rates out. So this is our mass balance on the concentration of the chemical in water. And I can show that to you. So let's define all these terms. So this is the water flow in. And C is the concentration of a chemical. So we're calling that a solute. And then V, of course, is our control volume. So let's say I take this first term here, number 1, and I'm going to look at that term And so we have volume times the change in, I keep trying to write a partial differential, volume times the change in concentration with respect to time. And if you look at the units here, we have the units, of course, of volume. So we just call that volume. And then we have the change in, we have mass per volume for the concentration and time for the derivative. So notice that even when we're working with derivatives, we can still work with the units in there, just ignoring the derivative. We have mass per volume or concentration on top, time on the bottom. And then you can see that these volumes go out and we end up with units of mass per time. And that's a mass flux. And then if we look at this term here, I'm just going to look at one because they're both the same term dimensionally. We have flow rate times the concentration, and that has units of volume per time for the flow rate. And it has units of concentration, which is mass per volume. And now the volumes cancel out, and we have units again of mass per time, which is again a mass flux. Okay? So now we know how to treat a mass balance for a solute, not just for the volume of water, or the mass of water, or even the heat of water.